Okay, so an example with damping effect. So a mass weighing 4 pounds is attached to a spring whose constant is 2 pounds per foot. The medium offers a damping force that is numerically equal to the velocity. Okay, that's going to tell us what the beta is. And then it says the mass is released from 1 foot above equilibrium with a downward velocity of 8 feet per second. Okay, and so those last two conditions are the initial conditions. Okay, so let's examine this. So the mass weighs 4 pounds. Okay. Now remember the question that we're dealing with is this. Okay. So we need to find MK and beta, all right? All right, so the mass weighs 4 pounds. Okay, so remember, this is going to be weight divided by gravity. So M is going to be 4 divided by 32, okay, which is going to equal just 1 divided by 8, okay? And so K, it actually gives us the spring constant. We don't have to find it. So K is going to be 2. Okay? All right, and then where's the beta? The medium offers a damping force that is numerically equal to the velocity. So if it was 7 times the velocity, okay, then your beta would be 7. So since this says that it's numerically equal to your velocity, what that's really saying beta is going to equal 1. Okay? So we have 1 over 8, the second derivative of x with respect to t is going to equal negative 2x minus dx dt. Okay. Great. So, but I want to get everybody onto one side of the problem. So let's just move those guys over. Okay. So we have 1 divided by 8, now the second derivative of x with respect to time, plus dx dt, plus 2x equals 0. Okay? But we're not in standard form yet because I don't want that 1 over 8 right there. I can't use the auxiliary equation at this point. So I'm going to multiply everything by 8. Okay? So the equation that I eventually get to is that dx dt plus 8 dx dt plus, now 16x is going to equal 0. All right. So now I can look at the auxiliary equation. All right. And like I said before, we're just picking a letter. So it's going to be L squared 8L plus 16 equals 0. Okay? And we can factor this one. So that's L equals 0. So L is going to equal negative 4 and twice. Okay? So this tells me that x of t is going to equal c1 e to the minus 4t plus c2 t e to the minus 4t. Okay? Okay, great. Now, where are we at this problem? Now we need to solve for C1 and C2. So if I look back at my previous statements, the mass is released 1 foot above equilibrium. Above equilibrium, that means that it's negative, okay? It's got a downward velocity, so since it's going down, it's actually headed towards the positive region. So that's going to be a positive 8. So x of 0 is going to equal -1, and x prime of 0 is going to equal 8. Okay? Okay, so let's do the first one. X of 0 equals -1. So -1 would equal C1 times e to the 0 plus C2 times 0 e to the 0. So that means that C1 equals -1. Okay. Now I'm going to have to take this guy's derivative. I'm going to have to do the product rule on the second one. So let's go ahead and take this derivative. X prime of t would equal, all right, now that's going to be -4 C1 e to the minus 4t. Okay, plus C2. If I took the derivative of t, I would just have e to the minus 4t. Alright? Plus, I'm going to write this one like this. C2t e to the minus 4t and multiply by -4. Okay? Alright, now we're using the fact that x prime of 0 is going to equal 8. So 8 is going to equal -4. Alright, C1 is just -1. Okay? That's equal to 0. Right? Now plus C2 e to the 0. Okay? Now plus C2 times 0 e to the 0 times -4. Okay? So e to the 0 is 1, e to the 0 is 1. So 8, alright, -1 times -4 is just +4, and then plus C2. So if I subtract 4 from both sides of the problem, I'm going to get that C2 equals 4. And that leads me to my answer after all of that. Negative e to the minus 4t plus now 4t e to the minus 4t. And that's the answer to our problem.